Right, so we'll start with an introduction to ANSYS for fluid flow modeling. That's going to be the topic for the discussion for today, new topic. So a typical workflow in any commercial or open source CFD code or a software is a 4-step process. The first one is to set up a geometry, and the geometry setup can happen in a separate software. You don't need the same commercial code to develop the geometry. In fact, geometry softwares are very different. You'll have a typical CAD software for developing the geometry, which can be quite complex if you want. Then once you have the geometry, you have to mesh it. I didn't write it here. So geometry and meshing, they go hand in hand. But once you have the mesh, you have now the discretized domain. So the next step is to, the equations, etc. are set up in the solver. That's available there. You have to set up the solver settings as to what options you want to choose in terms of the parameters, geometric as well as numeric. And then you have to also set up the boundary conditions to provide, because boundary conditions will define the problem here, in addition to the domain that you already have now meshed. So once you specify the boundary conditions and the solver settings, the next step is to run it. So you'll have a window where you press run calculation, and the things that were happening in a Python code that were happening in behind the picture, this time you will see the sort of residuals being plotted on the screen, and you can visualize things in a much better way. In Python also we could have done that, but the aim was to write a solver and run it, not to make it not to make the front end more pretty. So this is a front end that's available to you. And once the solver is completed, once you have run the problem until the designated time or till convergence, then you post process it. That is, you will plot the things that you require from the flow situation, be local fields where you want to visualize stuff, or be some sort of an average quantity that you extract from that simulation. Okay. So let's start ANSYS. So it's a commercial software, so license is required here. Now our campus has licenses available for classroom learning as well as research. So the difference between classroom licenses and research licenses are that the size of the problem. For classroom licenses, you will not be allowed to use beyond a certain size in the sense of number of nodes or the number of control volumes. That's because when you're learning something, you don't want to solve a very huge problem. You just want to learn how to solve the problem on a small grid. But for research cases, you will require a larger grid. So we have different licenses. So choose the one that suits you. The A11 PC lab has ANSYS installed, so you can use that, or you can install ANSYS on your own machine with the help of instructions available on the IT website. License verification happens through the license server of IIT Mandi. So you have to make sure that you are connected to the intranet of IIT Mandi, or you are connected to the VPN, and then that gives you access to the intranet. So it's you cannot use it if you are completely outside the campus with having no link to the campus network. The good thing is you can also run ANSYS on the HPC clusters of IIT Mandi. So that allows you to do solve large problems for research using the hardware, the complex hardware available on the cluster. So once you have set up ANSYS on your machine or on the HPC, the next step is to open Workbench. So rather than giving you a textual discussion, let's do it. So the first step is to open ANSYS Workbench. So let's. So in this case, I'm using a virtual machine. So I've installed ANSYS in a virtual machine that allows me to use it and share it with the research group if required. So in VirtualBox, I'm opening ANSYS as a virtual machine. So we've already done that for Linux-based machine, but you can also have Windows-based machines in Windows OS. There's no constraint on that. Right. So the first step is to open ANSYS Workbench. ANSYS Workbench is, as the name suggests, it's one-stop shop where you can include different projects and connect them. It can become quite intense and quite useful. So you can solve one CFD problem, and then the output of that in terms of some parameter goes into somewhere else. You solve a solid mechanics problem there, and then you bring it back and so on. So you can connect them through arrows and so on. But today we'll simply talk about a fluid mechanics problem. Okay, so you open Workbench, which look like this. Usually takes some time to load because it's quite a heavy software. Right, once we open Workbench, then we have to use a fluid flow workflow from the toolbox to start a new project, and then we'll have to set up the geometry. Specify what sort of geometry we want. So we want a 2D in this case to have a simple problem. We're solving the backward facing step that we had done in Python. Same thing in ANSYS today, and then we'll start with the geometry. Let's move this. So now I can quickly move between the pages. Right, so I'll pick this. I hope you can see this. Just drag and drop this here. So that is that visible from the back? I don't think I can zoom into this. So you have a workflow. I click geometry here, and then if I go to view properties, on the right hand side it shows me all the properties. So here there's a property, it's a tiny font here, but it says 3D. So I'll just select 2D here. So that tells us that it's going to be a 2D problem. So then I right click geometry, and then say a new geometry. So there are different software available to develop the geometry. I'm using Design Modeler. Yeah, that's one software available in the Workbench. Okay, so this is the geometry software now. So we're done with this setting up the Workbench. So the next we have to create a geometry. So since it's a 2D problem, so we are going to set up a geometry in an XY plane. And then we'll have to set up the units, sketch the domain, and then set up the dimensions, and then we'll have to convert that to a surface, because ultimately it's going to be a surface on which the problem is. So sketch is just a sketch with the lines, but you have to call or make it a surface out of it. So we select XY plane, a normal view of the XY plane. We are working in the XY plane here. The units this time are meter, which is fine for us. It's a backward facing step, so I'll make that backward facing step using two different rectangles. So I'll go to sketching here, and then we'll start with a rectangle. So I'm not worried about placing it correctly or the dimensions right now. I'll work with that later. So this was something like this, and these two were connected together. So let's set up the dimensions. So it's very much like a CAD software that you have seen in the past. So we have 4 dimensions, V2, H1, H3 and V4. So V2, which is the entrance length, was 1 unit, and then V4 was 2 units. the length H1 was 2 units and the length H3 was 10 units. I think that is what it was, and now I can make it a bit zoomed in. So you can see that they're not quite in the right positioning. So for that we have to give some constraints. So the constraint here is that this line has to coincide with this axis. Sorry, so there's a, so I have to make a coincident constraint. So this line has to coincide with this axis. So that brings the whole thing down, and then I have to coincide this line with this axis. So this now I've given some constraints, so that has brought it here, and now a constraint is that this top vertex has to coincide with this top vertex, and that should take care of the connection of the two. So I can sort of zoom again, and now you see that it looks like the geometry we wanted. Okay, is that clear? Right, next we have to clean it, because you can see that we have connected two rectangles. So what we have is the right rectangle is a complete line, but we don't want that complete line, so we want this to be a hollow domain. So these lines have to be removed. So for that we'll have to modify and let's see. So I select this and say delete. So that deletes the right edge of the left rectangle, but we still have this long edge that we have to split into two. So we'll call it, do it using trim. So we select this edge, say trim, and trimming will be done using this edge. Oops. Yeah. So now you can see that if I zoom into it, so you can see that it's been the center one is removed. The dotted line is simply the axis. If I remove it, you can see. Okay. Now there's plenty of help available on YouTube, on the internet for this. So it's a commercial software. They have help manuals available and so on. So you can go through it in detail if you want. This is a very quick discussion on this ANSYS. That's pretty much it, I think. We have set the dimensions. Now we have to make a surface from sketch. So let's do that. So sketching is done. So we'll go to modeling again and press generate. So we go to concept here, and there surfaces from sketch. So I select this sketch and say apply, and then generate. So now you can see that it's generated one surface. I can see one part, that's a surface body. Okay. That's pretty much it. I have to make that this is a fluid. So it says it's a solid, so I'll just call it a fluid. We'll save it. Let's do it on the desktop. So you can see there's a tick here, so that geometry part is done. So next part is meshing. So we have to open ANSYS Meshing and generate a basic course mesh. So I'll double click the mesh part here, and that should open a meshing software, which is a separate software from geometry. Now again, there are plenty of options available. You can do as complex a task you want, but our aim is to simply get you started. So you click mesh here. Typically what we'll do is we'll just generate something. It generates something like a coarse mesh. So let's see what it does. So it generates this kind of a very coarse mesh. I'm sure we don't want this. So what we'll do is we'll have to set the element size. Now this size is 1 meters. So I want around 10 mesh elements to be here. So let's make it 0.1. Okay, and then we'll generate it again. This looks much better. As simple as that. Okay, so this is a mesh done. So meshing is done. This face meshing I think usually is required. So let's say face meshing. Once we have generated the mesh, we have to now generate boundaries names because they'll be used in the solver. So let's define boundary name. So for that we'll say we have to select edges here. So we'll click the edge option here. On the left face, if I click and right click, it says create named selection. Shortcut is N. So I click this here. I'll call this inlet. So this becomes the inlet now. So it generates a named selection called inlet, which is this one. So I'll be using this in my solver. So next is on the right face, I click this, shortcut is N, and I call this outlet. The top one, well, it contains both of these, so I'll control select both the top ones and combine them into one called top wall. Then I'll have a lower wall. Then there's a step wall. Just naming them different, you can combine them into one if you want. And this one is lower step wall. Okay, so we have these boundaries. You can click it, click them all, select them and click them. So you can see these just to check things are right. Okay, once this is done, you save the project and close. So I guess this is already saved. We'll have to right click and update the mesh here. So it updates the mesh. Sometimes it will just show you things for preview, but behind the picture it has to update into a right structure file. So I've got quite a decent machine here. It may take much longer on your desktops. Okay, this one's a 13 generation processor, which has I think around 16 cores. So it takes slightly lesser time. Okay, so let's set up the problem now so that you can see the complete workflow here. So we'll make it a double precision. So that tells us that you will be using double precision for real numbers. And then we can increase the number of cores. So I'll make it 4 cores. I've got a multi-core machine, so it will help in solving things in a parallelized way. And then you start the solver. So now it will open the Fluent solver, where we'll be setting the solver settings and boundary conditions. Okay, so once we have updated the mesh, we'll go to the general settings. So you can see it's been able to import the domain correctly. It also figured out that there was an inlet, there was an outlet. So using the words inlet and outlet, it figured out that these are the boundaries that you want, and the others had a wall word in it. So it figured out that they were all walls. So let's go to general. You can always check and see if the mesh is fine. Sometimes you have hollow points and so on. I had that earlier in my mesh, so it showed an error in the check option. So will you be using a steady state solver? I want a steady state solution, and then there's no gravity here. Let's go to models. So viscous, right now it's by default given me a K omega turbulence model. I'll simply use a laminar model here. You can also use inviscid. It will remove the diffusion or the viscosity terms, but I do want viscosity here, so I'll keep it laminar. Then we go to materials. So in fluid, currently it has air. So let's double click it. The air properties are this, so I'll just modify them because we had a fluid with density 1 and viscosity of 10 to the minus 3 in our lab problem. So I'll just modify it here. It will only modify it for the current case. It will not modify the air properties in general in the software. So I just click change/create. So now it has set the viscosity value. So the kinematic viscosity now becomes 0.001. Then we go to boundary conditions. So for the inlet, we have to specify the velocity. So based on what Reynolds number you want, so we are specifying the normal velocity, which is from in the x direction. So that let's call that 0.05. Okay. Size is 1 meter, so the Reynolds number will become 0.05 times 1 divided by 0.001. So that becomes 50. The Reynolds number is 50, which is quite laminar in a pipe. So apply and close. Outlet boundary condition, it's a pressure based condition, which is fine, and the wall conditions will also be fine. So there's nothing to do there. You can check it yourself. I'm short of time, so I'm just doing it very quickly. And then we go to methods. Solution methods, what methods you want here. So here it says what are the schemes available. So SMAC is one scheme. This is not available here because we have better ones available. So there's a coupled scheme. It's basically pressure velocity coupling. So pressure and the predictor and corrector equations, they are both coupled to each other. The pressure and velocity are coupled to each other. So these schemes, so we'll be discussing the simple scheme in the next lectures to come, and the other ones are quite similar, but they have some differences. Then how do you discretize the pressure term? The momentum here basically means the convective term and so on. And once you have decided that, controls will give you an option for the relaxation factor. So we will not touch that here. And then you can have monitors. So some reporting plots and residuals. So it will, because it's using an iterative technique. Right? So residuals will have to be tracked, because residuals go down with time as you iterate further. So it's using some sort of an iterative linear solver here. So you can go to advanced settings and see what the solvers are and so on, but we are not interested in that right now. We'll just go with the default values. And then you have to initialize the solution. So we initialize the solution. Just a standard initialization with all 0 values. So that becomes the initial velocity and pressure values. And then it's good to have some animations. So I'll say that so if I go to plots, graphics, I can have a contour. So I can define a contour of velocity magnitude and compute and display it. So right now it's all zeros. And then I can go to animations. And here, since the contour is now available, I can select this, and after every one iteration, it will save the animation values. And then I can go to run calculation. And you can see it actually uses a pseudo time stepping. So it's adding a del by del t term, del phi by del t term, and it's time stepping. So it's using an explicit pseudo time stepping technique. So we set 1000 iterations here, and then you just click calculate. So now what it will do is it will show us the residual values here. So there are residuals for pressure through continuity, x and y velocities. You can see they're all going down, which is what we expect because we want things to converge. And now you can see that the velocity magnitude has converged. We can go to the animations now and play back, and you can just see frame by frame as to how the solution proceed. There's a lot more you can do here. You can plot vectors, velocity vectors to see circulations and so on. And you can also do a lot of post-processing, which is available in a separate post-processing software. If you want, I can quickly show you the vectors here because that's good for visualization. So we can see these vectors. I can actually zoom into this recirculation zone because that is what interests us, and you can see this kind of recirculation here. And if I had time, I would have shown you how to plot the shear stress on the bottom wall because we had defined a lower wall here. So I can show you, we could have seen shear stress, and from there we could see the reattachment length where the vortex reattaches and then the flow proceeds in the x direction again. So that's the size of the recirculation zone. So that's all for a very quick demonstration of the commercial CFD software called ANSYS Fluent. As I said, plenty of stuff's available on internet in terms of instructional videos on YouTube as well as on their help manuals. So please feel free to explore them. It's always good to start with something which is a minimum working example rather than starting things from scratch, which can be quite intense for bigger problems. You simplify the problem, use them standard help examples to set up, and then you can modify the option. Because there are many options available. If you start experimenting with all of them together, the chances are things will not work in the first few runs. So we'll stop here for today, and then I'll see you.